co-editor of Springer Tracts in Nature-Inspired Computing and Data-Intensive Research Springer Nature, and advances in ubiquitous sensing applications for healthcare elsewhere, etc. Furthermore, he was an editorial board member of Complex and Intelligence Systems Springer, Applied Soft Computing elsewhere, etc. He is a fellow of IET, senior member of IEEE and member of ISOC, etc. I would now like to invite Dr. Rajeshwari, our Dean Academics, to come forward and present a sapling to Dr. Nilanjan D. Thank you, Dr. Rajeshwari, for that warm gesture. And now, without further ado, I would like to invite Dr. Nilanjan D to begin the session on the bigger, the better.
So very good afternoon to all of you. So next 30 minutes I will talk about a topic, the bigger, the better. So we need to rethink this statement. So I think majority of you, with me that the bigger means it's always better. So okay. So let's start from a very primitive problem statement, computation of pi. So some student from VIT, they are trying to memorize the value of pi. So how many numbers? One student whose name is Rajiv in 2015, Rajiv Meena, he have a Guinness record. He able to memorize 70,000 numbers, decimal numbers, pi. So this actually proves the human memorization capability. So if you talk about human memorization, there are 4 different parameters. One is called recall, one is called relearn, one is called recognition, and recall, recognition, reintegrate. These are the 4 different parameters. So just to prove how good your memory is, and some Swedish scientists very recently in 21 they come up with a number which is 62.8 trillion numbers, and this much number they able to compute decimal points, and how many days? 108 days. So just to find out this decimal points. So this was actually to prove the superpower of supercomputer, and just to prove this is big data, what actually big data is. So to find out the circumference of Earth, what we required only 10 decimal points. To find out the Milky Way galaxies, how much number of decimal numbers? That is 32 decimal points. Now if you have 65 decimal points, the observable Earth, you can able to find out. So now think about the numbers which you already computed by the supercomputer and proving that this is big data. So what about this remaining 62.79 trillion numbers? So are these numbers scientifically significant? So we need to rethink. We are generating numbers, but those numbers might not be significant, scientifically significant. So basically, all these numbers which we actually able to find out in this way are nothing but a kind of pollution, generating data pollution. So the first question is, the bigger the better. Whenever there is I'm talking about bigger, is it better or not better? We need to rethink. Now, if you look into this image, I think they are self-explaining. If it is a bigger, it's not always better. So now coming to the next part, dark data. So if you go through the data, you will see 60% of data we never opened. So if you took any kind of example, say recommendation system, maybe the feedback, maybe any company's data, 60% on an average data which never opened. So nobody knows this data is a good data or it's a bad data because it's never explored. So that means 90% unstructured data never analyzed and 60% data which never opened. So these huge data is basically the dark data. Now talking about the second question, are they good data or bad data? So once we are talking about machine learning, we are feeding the data, we don't have any knowledge that 60% of the data which are dark data, we are feeding as a big data, but maybe doesn't make any sense. So they are good data or bad data. Now third one, as I already mentioned the terminology, digital pollution. So that means we are, the earth or the planet is completely filled up with all those polluted data. So I am talking about polluted data because the data might be redundant data, garbage data, extraneous data, non-contextual data, whatever the data is. So that's why this is the third question we need to be rethink. Now, if you talk about any machine learning algorithm, the intrinsic nature is hungriness. So all machine learning algorithms are, you feed more and more data, it will give you some result. So if you feed more and more garbage, automatically the output will be garbage. So if you feed more and more polluted data, automatically the output will be, if you feed more and more dark data, automatically the output will be, or if you feed more and more non-scientific data, automatically the output will be non-trustable. So that's why garbage in and garbage out, we have to keep in mind that whatever the data we are feeding, even if it is a big data, still we need to rethink, am I feeding the scientific data or not? So that's why always, it's always important to look into the target data. And target data means when I'm feeding the data, you have to think about the targeted data. Now, as I already mentioned, the bad data means these are the typical types of bad data. But the very first part of any machine learning algorithm, it should be the cleanness of data. You have to clean the data. But as the badness is different, badness might be inconsistent data, erroneous data, say maybe redundant data. So there is not a single algorithm which can solve all these issues. So that means what I'm saying is, there is not a single generic algorithm. If you feed all those badness, it will make it a good data. Because badness is different for every different data. So there is a nice statement which is called, all good data are look alike, but bad data are bad in their own way. So that means all the badness of the data is different. So that's why, how much data you require for machine learning? This is a very interesting question because application to application data is, requirement of data is different. Say for example, if you are talking about a survey data, you are taking the, the output, the inputs from the different questionnaires. So how many numbers of data is a good number? 376 as per the RAWSoft. There is a software called RAWSoft. In search, you can search RAWSoft in online. You will see there is this is the percentage of error. This sample size should be this, and through 376 data, you can actually map 20,000 population. That means you need minimum number of sample, which is 376 for questionnaire based study. Even if you are collecting 400 data, it's a good number to actually map with 50,000 data. But in machine learning, believe me, there is no as such heuristic or meta-heuristic algorithm which actually tells you that this much amount of data you require for this application. So we don't know how much amount of data we require. Okay, now talking about all these LLMs which we are nowadays everyone is talking about, this GPT and all. Think about behind this there is a data mining, and you don't know what type of data you are trying to mine. That data might be non-scientific, bad data, dark data, etc. So all how does all this garbage in, garbage out kind of applications is if you apply for LLM, how it works? This need to be revisited. Now, any deep learning is basically a memorization technique. You are having some certain points, you are trying to interpolate on another point. So this is the main thing. But the main advantage, or rather disadvantage of deep learning is it failed to understand the underlying relationship in between any data. The day when the machine will be able to understand the underlying relationship in between the data, many problems will be solved. That's why the major limitation of any deep learning framework, the underlying relationship in between the data, to resolve this issue, we need different types of variable data. So if you have a data for say Eiffel Tower, it should not be taken from a single angle, it should be taken from all 360 angles. So if you can feed your system all 360 angle data, variable data, instead of 360 from single angle, that will be much more robust system. So that's why variability is very important. So it's not about big data, it's about big, clean, variable data. So that is a very important point. So that's why it's not, that's why it's it should cover all different aspects of data. It should not be taken one kind of biased data. So the question is, talking about big data should be changed as it is not only big data, it should be big, clean and variable data. Then only any deep learning maybe framework will work fine. Now, how much time we actually spend for benchmarking? Means if you are trying to come up with a benchmark data, is it good or bad? It's always good. If you go for any kind of benchmarking, you are having the hand trace, but there are different scenarios. Say for example, in India, a doctor used to spend per patient how much time? Any idea? On an average, how much time? 1.8 minutes. In states, 21 minutes. And in Bangladesh, 48 seconds. So they are super busy. So in 48 seconds, they decide what type of disease you are having. They start diagnosing and they prescribe. So that means the whole thing, comes in their mind in 48 seconds. So actually, this is a report comes in Times of India. You can search it. So this is a crunch of time for the doctors. So if you ask the doctor to come up with a hand-drawn benchmark data, it's always not possible. So that means we have to spend more money and more time to come up with the benchmark data. But interestingly, the leveling technique, there is a very limited leveling technique and sophisticated technique. Majority of the cases, the leveling technique works fine for certain imaging modality, might not work for other modality. So there is an area where many researchers can focus that they can come up with a proper strategy of leveling. There is an interesting data set which is called ImageNet. So Professor Lee from Stanford University in 2009, long back, their group, they come up with a huge data set which contains 14 million data, where 80,000 distinct categories. So cat, mat, rat, hat, 80,000 distinct categories. Now talking about this particular data, based on that every year there is a vision computation, conference they used to organize. And initially during the period of 2010, shallow machine learning, the error rate was 28%. And you can see in 2012, when AlexNet introduced, there is a huge dip of 10% at a time, 1 year. So that means from 26 it's come down to 16. And now after ResNet, after 2015, it is lesser than the human error rate. And every year gradually it is decreasing. So you can imagine that every year the complexity of all these deep learning models are getting increased in this way, so that we can resolve this particular issue. That how difficult or challenging this problem is. Professor Hilton in 2012, he come up with an interesting article. He just find out 1,000 categorization, not 80,000, only for 1,000 categorization. How many numbers of parameters you require? 60 million parameters you need to tune. And how many numbers of intermediate nodes? 6.5 lakhs intermediate nodes. So think about the complexity. 1,000 categorization, you need this much. For 80,000 categorization, how many numbers of intermediate nodes and parameters you need to tune? So no such kind of algorithm, maybe optimization algorithm, will work very nicely for this kind of cases. So that's why this categorization problem or this parameter tuning problem is a big issue for deep learning. So that's why we used to say how complex the deep learning models are. Without knowing this, what we try to do, we always try to club two different deep learning models all together. Maybe with CNN we merge it some another model, and then we come up with a hybrid model. So interestingly, once you, coming up with a hybrid model without computing the number of hidden layers or maybe computing the number of parameters, it is something a disaster. Now, talking about convolution neural network, which is a very, you can say the first deep learning model, that time they started working on convolution models. That model having an interesting, property. In any layer, you will see there is a called max pool or mean pool. So that's called the pooling technique. So pooling means if you have a 3x3 matrix, you take the maximum and throw the rest. But who said remaining all those 8 elements or the 8 objects or maybe the 8 pixels, they are bad guys? Maybe later they can be good also. So basically pooling is a disaster of CNN. It's not actually my statement. In a AAAI conference, Professor Hilton said that CNN is fundamentally flawed because pooling is a technique which doesn't make any sense because you don't know the underlying relationship in between the data. Without knowing the underlying relationship, we are simply taking out the maximum or pulling out the mean value and throwing remaining. But the rest of the elements or the pixels, you don't know, maybe a good guy later. So that is one of the interesting point. Whenever you use any kind of CNN model, you should be, you should think about the scaling, the translation, the rotation property, and along with this, you should think about the pooling also, means how it actually works. Now, as I already mentioned about the limitations of data, so there are different scenarios where you will see there is a crunch of data. Say for example, there is a chronic disease, but the availability of the data is very, very less. Maybe it's a sensitive data and you will not be able to collect the data. That can be different reason. For different countries, they have their different, say, data privacy policies. Maybe the patient privacy laws are there. Even for the, there is a time constraint is a big issue for different, as I mentioned, for the doctors. So for this reason, the availability of the data is not always, you will not be able to gather more and more data. So machine learning model, as I said, it always demands more and more data. But there are different scenarios where small data can be an interesting research area. So if your algorithm is working fine for the small size data, that might work for the larger database also. But small size data is a very common problem. Now think about a medical problem where you are dealing with, say, 500 CT images, and other side, AlexNet, you are deploying on 14 million data. So same AlexNet you are deploying for 500 data, and same AlexNet you are deploying for 14 million data. Now think about this. So we always need more and more data. But again, that data should not be a kind of those type of data. So small data is the biggest issue. Now, one of the interesting solver of this particular problem is a weakly supervised learning. So it's not it's not, say unsupervised learning, or it's not a supervised learning, it's a kind of weakly supervised. So if you are an engineer, you can benchmark. If you don't have available data from the doctors, benchmark. So you can consider a delta error or maybe a heuristic mechanism you can come up with, so that by considering that error, a non-expert data can be, benchmark data can be also considered for as a benchmark data, just to increase the volume of your data. So weakly supervised learning is a kind of technique by which we can little bit, solve such kind of problem if you have a very less size of ground truth data. Now, why the small data size I am talking about this? Because people always think about big size data, but if the size of the data is very less, available data is very less, the variance will be very high. If the data availability is less, the data variance will be automatically high. Now there is a chances the machine learning models will get overfitted. There is a chances It can be, there can be outlier. So if there is a 50 data, one outlier, 5,000 data, one outlier. First case is something very vulnerable case. So that's why small size data having such kind of problem. Variance issue, overfitting cases and outlier cases. For these, that's why how your machine learning models are actually able to solve a small size data problem. Is it able to solve a small size data problem? Because machine learning models are good enough for large size data. But how it is functioning for very small size data, that needs to be also investigated. Now, talking about the synthetic data. Synthetic data is a very interesting data which you can, if the data, you don't have a kind of exact data, you are trying to come up with a fake data or is a kind of synthetic data, you are generating synthetic data which you can touch but the feeling will not be the same. So if the actual data having some legal issue, ethical issue, maybe some constraint is there to use that data, so you don't use directly. Instead of that, you can create a kind of replica or kind of synthetic data, and that data, on that data you can work, run your whole algorithm, whatever the algorithm is. So here, the model learning trainings are basically, the copyright issues, the privacy too, just to bypass all these things, people have a tendency to come up to create more and more synthetic data, which actually motivation of, generative AI. So once we talk about generative AI, maybe before that we talked about GAN and all, this model we are using for the, solving such kind of issues of creating synthetic data and all. So synthetic data might be the future of machine learning. Why I'm saying this? Because if you go through any kind of data dimensions, you will see almost nowadays again 60% data are generated data are synthetic data, where people are dealing with synthetic data. Because if you have a crunch of data, you create your own synthetic data. Do your operations, run your algorithm on the synthetic data, might be you are so close to the actual. So, if you go through any kind of geometric transformation, these are very old primitive technique for data augmentation. So if you have a, say, data size 50, you can create 500. So now look into this technique. If you go through any geometric technique, translation, rotation, scaling, maybe go for zoom in, zoom out, maybe stretching, shading, or maybe you can go for the contrast, stretching, or say, elastic deformation, or maybe color augmentation, you are changing and you're creating n-fold images. So from 50 images, you can create 5,000 images by rotating, translating, etc. Or maybe there are a few other techniques like random cropping. You crop randomly from an image, you create many images. Or maybe you change the variance level kernel. So if there is a Gaussian, so you change the variance level, you can create n number of images. And again, mixing, maybe blending technique. You increase the foreground and background and you can create many images. But think about it, all these techniques still now many people are using in imaging in imaging applications. But all these techniques are fundamentally flawed. Again, why? Because the reason is, if you look into the D image, the kernel filter, all those images, 3 cross 6, all those images, so basically are creating from the base image, fundamental image. So by changing the fundamental image variance level, you are creating another, say, 24 images. But all those images carrying almost similar kind of noise, almost similar kind of information. So it's a kind of redundancy. So whenever you are going for such kind of data augmentation technique, you are actually feeding redundant data, erroneous data, garbage data. You are upholding the sample size, but actually what you are doing, you are putting more and more redundancy in your system. So these all techniques, whatever we are till that we are using, are having limitation. So that's why this traditional technique to come up, get out from all this, there are some deep learning models. Like say for example, pre-trained model. Many of us use transfer learning model. So if you have a small problem area, you are trying to solve that problem. If you fail to solve that problem, you have an experience to solve a problem which you solve in a larger data set. So that experience you feed as a transfer knowledge or as a frozen knowledge to solve the problem which you failed to solve. So that is called the transfer learning model. So if you have a very limited data, you try to solve that problem for ImageNet data because that is huge data. Now if you have that solve experiences, that experiences you can share with the new model. And in this way the transfer learning model actually works. We know all this, means how these models works. But think about this ImageNet data. Based on the ImageNet data, you are actually fetching the frozen knowledge to solve another problem. But ImageNet data, which is a 14 million data, 80,000 distinct category data, which is again a fundamentally flawed data. Why? The reason is, if you look into the chairs, ImageNet, all chairs are good looking chairs. They are taken from a proper lighting condition, proper angle, proper shape, they are all organized. But in your home, not in the seminar room, currently it's all our ImageNet database, but at our home or classroom, the chairs are messy. I mean, it's something not taken from all proper shape, lighting condition. So, theoretically, ImageNet data are all so-called good data. But in real life, ImageNet data not works because they have taken only good data, not consider the bad data. So based on that, if your whole model, transfer learning model you are trying to design, so you are doing that based on the good data. You never tested the bad data. So that means if you never tested the bad data, that means ImageNet itself is a collection of good data only. So that's why I'm saying, so this is another interesting point. So transfer learning model, based on what you are doing, transferring or frozening the knowledge, you need to rethink that are they good data? Are they only sharing the good experiences, not the bad experiences? During COVID, one country claimed that we don't have any infected patient in our country. So what you will conclude? You will conclude that, okay, interesting part, I mean, they have some strategy to come up, I mean, to cope up with this situation. Actually, in reality, there was no testing. So that means machine learning models fails because they never tested. So there is no 1, no 0, so it's all passed. So here also, all good data are there for transfer learning models. We generally used. And we say, okay, we are getting good result, but we never tested bad data. Now, how robust all these models are. Every day there are new deep learning models are coming out, and nowadays everybody is starting, I mean, claiming it's my own name and I am coming with a deep learning model. So just tuning those parameters are in. Because 60 million parameters, you can change anytime. Now the interesting paper comes in PCE a few years back, in 19 only. So they able to identify one particular pixel. So if you remove one pixel from an image, a cat will be dog, or a dog will be hat. So this is called one pixel attack. Very interesting work. You can go through this particular work and you will see that one pixel can make the difference. So that means it's a one pixel attack can change the whole model. So I'm talking about the pixel. So that is, it's good enough. Machine learning models are good enough. The deep learning systems are good enough for quite large fraction of cases. But it's again need to be revisited. We are only chasing the numbers. Every day we are talking about 99% accuracy. But we need to stop and rethink that whatever the models we are using, are they clearing all these queries or doubts? Now there is another thing that once you are talking about 99%, every day they are chasing 100%. Say maybe, I mean, not looking into the ROC or AUC, they're simply reporting the accuracy. So the next question is the trust issue. Why should I trust you? So from there onwards, people started thinking about the explainable AI. So your model needs to be explainable enough. So I think many of you are working in explainable AI, where from the linear model, say rule-based model, how the name-based, from name-based to support vector, maybe support vector to any kind of deep learning framework. If the complexity of the model increases, how the performance is getting, I mean, accordingly changing. So you are trying to, I mean, find out the explainability. You are trying to find out the explainability as well as the transparent model. How can you explain, interpretable, etc. So in this way, your model is giving more and more better performance every day, and the transparency or the trust issue is always there. So this is another biggest issue. Now talking about the emissions, I mean, we are all talking about the SDG goals, and one of the goal is zero carbon. So once we are talking about zero carbon, now think about it. So if you run a car for 7 kilometers, maybe it is equivalent to a CNN model of 7 layers. So the same amount of carbon it is emitting. So if the scenario is this, if you think about a huge deep learning model where there is so many hidden layers and you are coming up with a hybrid model, now think about how much carbon is emitting. So now nobody is asking about space complexity or say time complexity. People are more cautious about knowing what is the carbon footprint of your model. So any deep learning model, there should be a dedicated part where you should report that how much carbon the model is emitting. So this way, how the carbon footprints, and now interesting part is, if you are talking about these LLM models, now think about the carbon footprint of all these LLMs. Because if it is a huge, large, the word is large itself, so that means emission needs to be checked. Now what's the future? I'm not promoting this book, just to show you that, one dimension is you directly work with the raw data, and another way you can create your knowledge or wisdom from that data itself. So once we talk about data, maybe in future it's not only data, maybe data knowledge management can be fused together to solve different issues. People have started trying these DKM models. So how much effective these all DKM models are, machine learning models? There are very few, very limited works are there, but still this is a new area where people are working and thinking about to fuse the knowledge and data both driven. So it's not only data driven or might not be the knowledge driven, if you can combine these two. So the interesting part is, there is a book by Martin, it's a very small book, but a very interesting book, Small Data. So any invention, actually, if it can solve a problem which is a small size problem, you will see in prototype way, you can solve a bigger problem also. So in this way, what I'm trying to say is that nowadays, once we are dealing with machine learning models, the lucrative numbers, it's always good, but we need to think about it. One, say pandemic teaches us, in 2020 we solved the COVID problem with 100% accuracy from CT images, but in reality it takes another 2 years. The reason is, your algorithm might work fine for North Indian patient, might not work for South Indian patient. The reason is, might be work for Japanese patient, might not work for European patient. Because if you look into India, say the map, you will see, if you go from north to south, the curry, only one thing, curry is getting diluted. So North Indian curry, Middle India curry, South Indian curry, you will see curry is getting diluted. So in this way, the food culture is different, the ethnicity is different, the alcoholic pattern is different, the smoking behavior is different, sleeping pattern is different, everything is different. So you are working with a data set taking from Pune, and you are deploying that one machine learning model on that data set, and you are saying 90% accurately I can cure this particular disease or can detect that disease. That doesn't make any sense, because it might not work for the Japanese patient who might be taking some omega-3 additionally, or might be someone is taking, say, burger too much, or so this happens. So that's why it's all data dependent. So that's why you need to think about the usage of data. It's not always bigger the better. So we need to rethink. Thank you very much. Okay, I have one more slide to do. I thought it's completed. So the AI future might not be the more data, might be the less data. And I am actually nowadays working on small data only, because big data, there are so many people who are working on big data. I am more interested in working with small size data, because my area is medical science, medical imaging. So there crunch of data availability. So if I am having a patient at my home, I have to take permission from my parents also to use their data. So it actually begins from home. So that is the one thing. And last, synthetic data is all good. 60% data is synthetically we generated. We created Mona Lisa, we created many things, rows and etc. But ultimately, we need to think one interesting point, is my fake data is real enough? If it is real enough, we need to stop somewhere. And we need to rethink again that where we need to stop. It should not be the world full of synthetic data and full of fake data. Okay? So lastly, how real the real enough? So any lies, to establish the lies, there should be some data. And that data should not be lie data, because lie should not be based on another lie. Thank you very much.
Thank you, sir, once again for your insightful presentation. We now have some time for questions from the audience. If you have a question, please feel free to raise your hand.
No hands?
Thank you, sir, for sharing your expertise with us today. Your presentation was both insightful and inspiring. Your discussion has truly given us valuable perspectives to consider. As a token of our deep appreciation, I would like to invite Dr. Roshni Raut, General Chair, ICCUBEA 2024, to come forward and present a memento to Dr. Nilanjan. I request Rajeshwari ma'am to please come on the stage. She's there. Okay. Thank you, Dr. Roshni, and once again, our sincere thanks to Dr. Nilanjan. And now